saying, but essentially, when you talk about these two components of the decision problem, basically being the probability, the prior probability of beliefs about the states of nature, and the utility function, how can we be sure, or how can we be reasonably sure that something like that even exists? Okay, somebody can, given enough work, somebody can in fact assess those things for a given problem. So there's existence is something which is a problem, but there is a lot of literature in that area. Professor Savage, Jimmy Savage, and de Groot, and other people have been working on that kind of thing a long time. I've worked on this problem a whole lot. What they do is they provide a relatively weak axiom system on the revealed preferences of the decision maker, which ensures the existence of probability and utility both. We'll not go into details of that because that's a whole area by itself. If you want to spend, you could easily spend 4 lectures on that topic itself easily. Well, I don't think I want to go into that. But one point worth mentioning is that just like Surekha said that she is the grandchild academically of Professor Zellner, I'm the grandchild of Jimmy Savage. De Groot was a student of Jimmy Savage. His PhD was under Savage at Chicago, and then he came to Carnegie Mellon. And so essentially, I have my lineage going to Savage at least, and I'm happy about that. So there's a lot of work in this area. The axioms are basically fairly weak, except one axiom which people debate about a whole lot is something about, can we separate the probability and utility from each other, basically. Some people believe that what you have is a weight function, the product of the probability and the utility together, okay? But you need an extra axiom to separate them into two pieces, and there's debate about that. And if you're interested in those kind of issues, obviously some of the work, de Groot's old book on optimal statistical decisions and Savage's foundation statistics, and also the other work later on. Teddy Suttonfeld is one of the persons who have worked on this kind of problems. One can go into that, but that's not really decision making. It's not like philosophy. Okay. So let's keep away from that for the time being. So there are also other concern that some empirical evidence that individuals do not necessarily follow these axioms. They are weak axioms, but sometimes the people err. Okay. And de Groot and Sire in this book called Bayesian Analysis of Uncertainty in Economic Theory. It's a book published in '87, de Groot and Sire. Basically, it's a collection of papers put together into some very cohesive fashion, discuss these issues, and they address this issue about whether or not and how to worry about people don't follow the axioms. But one of the things they say is that the audience we're talking about decision makers. They're already well-trained people. This is not a person out on the street who doesn't know anything about probability at all. So they can be trained. If they're not well-trained, they can be trained to follow the rational behavior axioms kind of thing. And therefore, we'll not worry about that issue because these kind of problems will not be dealt by ordinary human beings. We're talking about people who are already trained in probability and statistics, and they understand the underlying axioms of probability. Therefore, if they don't follow the axioms, they can be trained to follow the axiom. Okay, that's their take on that. Now, there is a large body of literature on developing priors, reflecting non-informative priors, called non-informative priors, ignorance priors, or basically saying you have no specific preference for any data, okay? And based on your beliefs, therefore you want to use some non-informative prior. And Professor Zellner, I believe, is going to talk about that topic in his lecture, so I'm not going to even touch that. Basically, we're saying if you don't want to spend too much effort in assessing your all your body of knowledge about this problem, well, you can use one of these priors and still do a good job, better job than what you will do without going through this paradigm, okay? What it provides to, remember, it provides to you a unified framework for every problem, basically. So that's what is a great thing you have available here. So even if you don't want to spend time in assessing your state of knowledge, you can use these priors and do a good job and at least be within the framework. Now, assessing informative priors based on a series of quantiles or moments is something, a lot of work has been done in that area also. And if you're interested in that, certainly I can provide you some references. In fact, Professor Zellner's paper already has some references to that too in his paper available. Something which
one thing you want to mention is that these procedures could produce diffuse and informative priors.
right, both. Depends what constraints you put on the right. What constraints you put on the prior information now. Under certain constraints.
Moments and things like that.
Right. Now, there's one area which is a very intense investigation. These are called Bayesian networks. What this does is, and I said I'll give a tutorial on that next time around, is basically it talks about how do you simplify the procedure under which you can specify dependencies on conditional independence of collection of variables in this set of x and theta given the variables. Basically, it's trying to specify this through a network structure, and I'll give a tutorial on that next time around. Basically, that gives a recent tool, and it can solve large problems. I'll simply talk about something, what the underlying structure is, how do people go about solving this, assessing priors, through that kind of approach, okay? So we'll skip that, but that's something is under, both in computer science community and also in AI community. That's the area which is very, very popular these days. I'll skip that too, okay. Now, the criticism you get of Bayesian approach is that based on same data, right, people can make different decisions. Well, so what? Basically you have same data, but you perceive the information data differently too. Individual looks at the same data, but their perception is different about what information is there in data, right? So if they end up making different decisions, well, that's fine, because one should allow that, because essentially you are not ruled by a monarch who says, well, if you have this information, you make this decision, right? You just don't do that. And therefore, that criticism is not very valid, especially in decision making. It may be something, different point of view, different point in scientific inference, okay? But as far as decision making concerned, obviously each manager is going to use the data and their own intuition about the problem to make it take a decision, right? And the decision may be different from manager based on the same experiment. Therefore, that's because the manager is a smart manager, is going to use all the information, all decision maker are going to use all the information they have available from the data and for what they think they know about the problem to take a decision. A decision is different, but that's all right. There's nothing wrong with that in the decision-making framework. So that's where individuals process the same information differently. And, well, there's a nice quote here, says, to think is to differ. So obviously, if you're going to think in person, you're going to differ from other people, and there's nothing wrong with that as far as I believe that's fine. And that's a quote from Clarence Jarrett saying, well, hey, if you're going to think about a problem, you're going to differ from other people, and that's okay. Don't worry about that. There's a little small quote here. A smart decision maker will always engage in a creative process, okay? And what's the process? Any thinking process which solves the problem in an original and useful way. So you don't want to use automatic procedures, canned SAS procedures to solve your problem, okay? Because they're not necessarily going to answer the actual problem you have, or actual question you have. They're going to solve something else for you, and you don't want to do that. You want to think about the problem first, and then solve the problem in a useful way also, which is something original to you, okay? And then, here's the most important thing I would say about decision making and the modeling and everything else. What is most important is not the answer, but the question itself. This is a quote from way back in 1830s. I seek not to know the answers, but to understand the questions first, okay? This is somebody head of a temple in China in 1830 talking about, try to understand the question first. Once you then do that, everything else becomes much easier, okay? And that's where the Bayesian framework allows you to create all those inputs into the problem and then solve the problem. Otherwise, you can't do that because you're using some off-the-shelf procedure which is not necessarily answering the question you actually want to answer, okay? This is about just a sort of introduction framework, the whole thing. Now, I promised to you basically one application which is very much akin to what de Groot has worked on. And one of the things in his book, which I mentioned here, the book by Sergeant de Groot earlier, In the introduction, de Groot and Sire say something like the following. Most attempts to deal with uncertainty has been designed to finesse the problem. I mean, usually in economic theory, people write the problem up, then make an assumption, they put the uncertainty in the problem, but then they make an assumption which makes that things go away. So it becomes a certain problem, they solve the, what's called the certainty equivalent of the problem, okay? That's the solution to the problem. But that does not necessarily really, it's finished the problem now, but not actually solve the problem. And he gives an example of a famous Carnot's equilibrium solution to the two firms selling mineral waters from same spring. No cost, linear demand curve, okay? So demand curve is of this sort, A minus B, and these are the quantities of the Q and R are the production for each of the two firms, how much they want to sell. Firm's I revenue is the demand, P times the production they have, PQ. Firm 2's risk by P times R is their production, so P times R, this is the proportion basically, this is the demand here. Now what happens is Carnot gets this famous equilibrium solution, basically A over 3B, A over 3B, but both firms having same value here, based on the assumption that the rate of change of the Q and the R, based on what the other firm does, is not going to matter at all. It just assumes it's zero. But that's how he finishes the problem. The problem becomes deterministic because this part, when you try to find the optimal solution, take the derivative of this quantity with respect to Q and R, these things appear here, he assumes they're zero. So that's how the problem becomes solvable. But what de Groot and Sire do is essentially look at the problem where these things are not zero. Okay, but then they try to do different scenarios under which you can get the solution which is Carnot's solution based on still uncertainty in the problem. Okay, so that's what is this. Just a couple of papers there. They talk about that kind of thing. Basically, getting same solution or different solutions, but where this thing is not assumed to be zero. That's the kind of thing there's several chapters in the book which deal with this kind of how to handle uncertainty in these kind of problems. I will not go into that today. What I want to do is, in the book they also talk about several things basically which are useful from the economist's point of view. They talk about multi-period control problems, duopoly problems, okay, they have been discussed in the book. What I'm going to do today is just not go over multi-period problems, basically they're much more complicated. I'll just simply look at a version which is one period problem that gives the flavor of two agents decision making in this lecture. Basically, we'll talk about a very simple problem, one period problem, with the two agents, and they're going to make decisions about certain phenomenon, and how do you design your experiment so that you can reach some consensus decision in that situation. Let me just introduce the problem first, very quickly, what the problem is, and then so. This is not exactly what Professor de Groot has handled in his work, but it's very much similar in spirit. And this is something very much borrowed from Professor Lindley and Singapore Ballast paper in 1991, JASA, where he talks about what is the evidence you need to reach consensus action between two adversarial decision makers. So there are two decision makers, the adversaries, but you want to conduct an experiment which will hopefully lead to a decision which is agreeable to both the parties. Okay? So that's what I'll talk about. But it does bring out pretty much all the components which you will see in these kind of settings. So it's not multi-period, it's not very complicated, but it gives you the flavor of what you have. So what is the formulation of the problem? The formulation is you have two decision makers. You can think about those guys in simple terms, like M is a manufacturer, is a producer, a supplier, and C is a consumer, the buyer. So those two decision makers, okay? And they disagree over the quality level of a product, okay? Because they have their own perceptions, therefore they will not have similar some views about the quality level of this specific product you're going to sell to them, okay? However, the manufacturer is willing to carry out experiments to convince the consumer, right, about the quality level. Hopefully, by doing some experimentation, they have different beliefs, but doing some experimentation, they can agree on, after the experimentation is done, based on their own beliefs and the experimental evidence, they can decide whether or not the consumer will buy the product. Okay? So So that's the problem I'm going to just discuss here, because that gives you the flavor of kind of things you have to worry about in similar situations, right? So since M is the manufacturer and he's going to try to convince the consumer to buy his product, so the question is, how should M select the experiment, which gives him the best chance of convincing the consumer that M's view is more closer to being correct, because M thinks his product is much more high quality, consumer doesn't think so, and so through experimentation he's trying to convince the consumer that he is pretty much correct in what they are saying, okay, what he's saying, okay. So problem is, obviously you have to take into account the cost of experiment, because with your experimentation you're going to pay certain costs, you're going to destroy some samples, and therefore it's cost involved, labor involved, and you want to take that into account. If you don't do that, then obviously you can do enough experimentation which will either convince or completely let the consumer go away from you, because your product is really bad anyway. You don't know what you're doing to begin with, right? So that's why you have to take into account the cost experiment into consideration. So examples, pretty simple examples. M is a drug company and C is the FDA. FDA is a regulatory agency, and M must convince C that the drug is worthwhile, okay? But C demands evidence about several features of the drug, because FDA says, I'm not going to approve the drug unless the drug is better than the old drug, has no side effect or less side effects, basically. There are several dimensions which are involved there, and now the manufacturer has to provide evidence to FDA to convince the FDA to approve the drug. Okay, that's the kind of example setup you can think about. So what experiment evidence will best convince C, considering the cost of M? Okay, the cost is that which you have to take into account, and once you do that, you might reach a conclusion before you do the experiment that probably it's not even worthwhile trying to convince this person, because no matter how much money I spend, I won't be able to bring that person closer to my point of view, and therefore it's not worthwhile to do the experimentation at all. That's part of the option available. Okay, so second example. Manufacturer M is trying to sell a product to consumer C, and C can accept or reject it depending on evidence supplied by M. So whatever evidence comes through this experiment, C can accept or reject the lot, basically. Sampling, inspection, counting, right? Scenarios where you are the plans are being devised so that you can convince the consumer that quality is above the minimum acceptable level. Okay. So what is the formulation? Well, in this case, what's the action? Action is the consumer will decide to accept or reject your lot, right? That's the action you can take. So consumer's decision is to accept or reject. What is some action on the part of manufacturer? Well, prior to experimentation, consumer has certain beliefs about the state of the quality level of the product. That's consumer's prior information about data, and his utility about accepting and rejecting. The two decisions, accept and reject. So for each of them, there's a utility function for the consumer. Okay, for the consumer. Manufacturer has their own prior beliefs about data, and they are probably different, obviously. If they were same, probably wouldn't worry about much anyway. They're different, and they have their own utility function here. But here, this is the decision of the consumer here. For the consumer's decision, whether or not, if it is accepted or rejected the product, then this utility also takes into account the cost of the experiment at the same time, because obviously if he collects more, if he tests more samples, it's going to cost them more. They should account that into this utility function. The UM also accounts for the cost involved in the testing phase. All right. So that's the formulation. These two things. Decision is basically of the consumer. Manufacturer can decide whether or not to do the experiment, and if you do the experiment, how many observations to take based on the cost involved, right? So what is the assumption involved here? Assumption is that M and C agree on the likelihood function. At least that's agreeable to both of them. If I do the experiment, I'll observe the X, whose distribution depends on theta, and they both agree on same likelihood function. Otherwise there are problems, basically. So the same model for the data distribution given the All right. So you can think about it basically if there are sample inspection plans, you have n observations can be observed IID given data, inspect any units from the lot. Okay. After the experiment is done, experiment E is done, whatever it specifies how many observations taken, whatever else is done. This is specified. After experimentation, the consumer's prior is updated this, the posterior of the consumer, right? The manufacturer's prior is updated the manufacturer's posterior distribution. Right? That's the step involved here. So basically you're then updating both the current level of knowledge of these two guys is represented by the posteriors after the data is collected with the observation X. Right? Once you have that, then C chooses to accept or reject the lot. In this case, not to decision, basically accept or reject the lot based on maximum expected utility of his or her decision. So basically what is he going to do? He's going to look at basically two decisions, accept or reject, make the decision based on maximizing of decision D, this quantity. For each decision, he has the utility of C. This is the current state of knowledge of C. Find expected loss, expected utility, maximize this quantity over D, take the decision. That's the decision made by the consumer based on his current state of knowledge about the quality level and his or her own utility. When the decision is made, so what is the expected utility of this decision to the manufacturer now? Because this is the decision made now by the consumer based on the current state of knowledge of the consumer. All right. For the manufacturer now, what's happening? What does he get now? This is the decision of the consumer now, based on data you have, and the experiment E you have done. Your utility based on experiment E, the observed X, the state of nature theta. So this E tells you basically how many observations maybe. Okay, so that's what the cost will be involved here. The cost of the thing X you observe, theta is the true state of nature, and this is the decision of the experimenter, of the consumer. Sorry. So consumer decides to accept or reject. So this utility function depends on whether consumer accepts or rejects. And then this is the state of knowledge of the consumer, of the manufacturer, sorry. And therefore, that's what this person gets. M warrants this cost here, okay? M now chooses experiment E, which maximizes this expected utility. So M's decision is based on basically what he or she is going to see based on consumer's decision. And then now, question is, what E should I choose? How many observations test? Should I test at all or not, right? All those become part of the E specification here. And choose the E which is maximized. Basically, this is the part which is here. That part here, right? And then, since you haven't done experiment yet, you're doing pre-posterior analysis here by saying, I'm going to average this quantity with respect to the distribution of X now, the marginal distribution of X. And this is my expected utility before I do the experiment. Basically, the pre-posterior analysis, which will be done by the manufacturer to then choose the experiment. So PM X given E is simply now the marginal distribution of data given X. So this is the data distribution. This is the prior of the manufacturer, and this is therefore the marginal distribution. So you average this consumers benefit over all possible X's that can occur, because you have not done the experiment yet. Therefore, you want to assess now before the experimentation, what should I do? And therefore, you're averaging that the manufacturer's benefit with respect to all possible X's you can get in the experiment, and that is your what you want. You choose the experiment E, which will maximize this quantity. Is that clear? The setup basically, all right? Now, given that. So this is the basically two-action problem, except reject. You could have more than two-action problem too, because D doesn't have two actions. Basically, if you have more than two actions, you're going to see this is general setup where you have two adversaries, but then you're trying to, one is decision maker, other one is trying to plan to convince the decision maker to bring the person towards their own point of view, if possible, because it's possible that no matter how much experimentation do is the two views are so far apart, they're not going to move closer at all. In that case, you will say, well, there's no point doing any experimentation. Okay? So just now, to apply that very simply, just as an example, what actually happens. So assume now you have Bernoulli like basically you test items, n items, and some of the items will confirm the quality, others will not. So you get 0, 1 observation, you get defective, non-defective, or confirming, non-confirming items. Okay. So basically, you're assuming now Bernoulli likelihood. M takes a random sample of size n, where n could be 0 possibly. Okay, because that's the option available to you as part of deciding now should I do the experiment at all or not. Okay. Each xi is just two states, confirming, non-confirming, defective, non-defective, and so on. And fx given n and theta. N is an experiment, sample of size n. If I do it, binomial x and theta. That's the likelihood. This is what they agree on. Both the consumer and manufacturer agree on that we're going to test n observations, and whatever that happens on observations, whatever outcome happens, they'll update their state of knowledge to the posteriors and use those to make the decision. And basically, in this case, you're assuming that at least the two parties are willing to talk to each other. They're not going to hide their utility functions. If they're going to hide them, then obviously they can't really work in a kind of cooperative fashion at all. So that's the assumption underlying here is that the two parties are willing to at least cooperate to reveal their preferences so that one party can decide whether or not to even do an experimentation, or is it worthwhile to do any experimentation at all. Okay? So for simplicity, assume that prior distribution beta distribution here for consumer and a manufacturer both, so that you can. All right. So here this simply says that consumer or the manufacturer is much more has less variability in the specification over here. Okay, in the prior specification, because they know more about the quality of the product than the consumer does. This is bigger than that, and also you can say on the average, M has a higher opinion of the quality than C. Therefore, this quantity is less. This is there. What you're mentioning here is this is less. Therefore, this X here being measured is a non-confirming item, right? Yeah. Whichever way. Okay. So essentially, you have this constraint on these parameters because M has a higher opinion of the product than the consumer does. That's why you're trying to bring consumer towards your point of view. If consumer already was more convinced than you are, you don't need any experimentation pretty much. You can just, they'll buy your product to begin with, right? So essentially, with these two things, you assume it there. And now, once the data comes in from this experiment and observations, if n is 0, what happens? If n is 0, you simply these are simply the priors. If n is non-zero, whatever x you get out of n trials, that updates your posteriors given for both the consumer and manufacturer in this fashion. Once you have done that, so essentially now at your point, you know this quantity, but if x was observed, and this is you can do for every x what the corresponding posterior is going to be, right? Okay. So what you have is for consumer's utility for accepting the plot, given the quality level theta. Given the quality level theta, basically, this is the consumer's utility for acceptance, and also for rejection. These are the two actions: the accept and reject action. Basically, for each of them, consumer's utility function. And suppose you have to know that too. What utility consumer will use. Okay. C will accept if what happens if this one is. Obviously, this is a higher utility on the average, therefore accept that quantity, otherwise reject. So essentially, knowing these two things, you can now know for each x what will be the C's decision, right? For some x's, C will reject. For other x's, C will accept. So basically, what will happen in this situation, you'll end up with this situation where for x large, if you have out of n trials, you have a large number of acceptance, a good product, the consumer will accept. For x small, they'll reject because, in fact, the evidence from the experiment may have moved the consumer away from your view anyway, because essentially you really produce in the test fewer confirming products than you said they will be basic. Right? So essentially, this is the optimal decision, and what you can convert this region into basically x less than equal to constant, accept, x bigger than constant, reject. So here, x is really the number of bad product components. Okay, that's why x less than equals to c, you accept the thing, x bigger than c. So you can convert this decision making into some kind of cutoff point, which depends on what? The c will depend on basically n. C will depend also on these utilities basically. But you can convert the whole thing, this rule, into this kind of rule. Okay, once you do that, what does the manufacturer have now? For a given this rule now, which C depends on all this things going in here, manufacturer has to introduce two for M, for acceptance by the consumer and the rejection by the consumer. So for a given N, theta, and X, these are the utilities of the manufacturer. M's, these are the M's utility for acceptance or rejection action of C. So action is by C, but what does M get from that? Okay. So M's utility depends on X and N because M is going to pay the cost for the experimentation. So N is large, it's a large cost involved. Therefore, this thing also involves the N, which is accounting for the cost to be paid for the experiment of size N, right? Whereas here, in this case, N was not relevant. This utility didn't involve N at all because the consumer doesn't care. I mean, basically he's going to reject, accept depending on which is higher expected utility here. But this posterior depends on N now. Depending on how many units you test, this posterior is going to be changing with N. So, whereas in this case, this function will involve N itself because it's a cost, accounting for the cost by the manufacturer. Okay. So for a given N, for a given experiment, for N could be also 0. M's expected utility prior to experimentation is given by now what? You are going to average this quantity. I mean, this is the quantity basically looking at the inside integral here. The inside integral here, this part here, is the utility, expected utility of the manufacturer given a fixed N. Now this is averaging over different possible X's you can realize if you do the experiment. So you're doing pre-posterior analysis here, trying to decide if I get a certain X, what will consumer do, and then what would I get in return for that? What will consumer accept or reject for those X values? And now I'm averaging over acceptance region, rejection region of the two actions of consumer, and then that's my benefit at this point now. Okay. So M now needs to choose M that maximizes this value here. I mean, this is. I mean, now you can see all the components there now. Basically, N could be 0. If N is 0, then most likely consumer is going to reject everything anyway. Most likely because consumer is not convinced based on a priori specifications that you have good quality of stuff. So basically, for each N, once you have this specified, once this is available to you, you can, I mean, this could be the optimal solution reflecting the point that it is not worthwhile to attempt to convince C of the soundness of M's view because in this case, I mean, FDA cannot really, and then drug manufacturer cannot convince the FDA with any sample size because FDA thinks you really have bad stuff. Don't even come back to me at all because what you're trying to sell to the consumer is just not worthwhile. In that case, it's not worthwhile for drug manufacturer to spend any time, any money to even do any testing at all. No clinical trials. Okay, basically some of this thing happen at the early phase of clinical trials where things are rejected. The product, the compound doesn't work very well in the case of animal testing. So it doesn't go to human testing at all because it's just too expensive to do testing, and FDA probably won't get convinced anyway, so why do it? Okay? So this is the option available in different other N's which are positive, and then you want to simply choose the N which maximizes that. Okay, just a simple thing, just to see what this things could be easily solved once you specify utilities basically. This is a simple example again from the paper. The leasing Purwala paper. For consumer utilities, basically it depends only on theta because that's what it depends on, right? You see a theta is simply saying if theta goes up, acceptance utility goes up. It's a better quality product, consumer is happy about that, it's going up. If it rejects, well, it's whatever, it is a constant value, doesn't depend theta at all because we're saying that in this case, once it rejects, it doesn't care. Whatever quality level was, maybe some kind of opportunity cost which you're losing out, okay? But this doesn't depend theta anymore. And essentially, these constraints come from this being reasonable utilities. Basically, A1 is bigger than A3, bigger than A1 plus A2. Because the theta is equal to 1, that's when this theta is equal to 1 simply says what? It's really a bad product completely. Okay, theta was measuring bad, sub-proportion of bad products. Okay, so essentially, these constraints come out. A2 is negative. If theta is increasing, it's a bad and worse and worse product. Therefore, you don't want to accept that at all. So A2 is negative. For theta known, acceptance occurs, but theta is so basically for theta known. If you knew theta, this is the cutoff point. But you don't know theta, you have basically prior distribution or posterior distribution over theta. So this is a break-even value, okay? If theta was known, we don't know the theta, so you have uncertain. So you can think about spectral size n. You can assume that if you assume this is the consumer's utility, A given theta is n r 1 minus theta n minus n. This is basically coming from this with some reasonable things put in there for A and B, and that becomes utility for using specific A, B, A1, A2, and A3. And then for this, the theta break-even value is this, but you don't know theta again at all. So you have to take into account the uncertainties about theta. If you know theta, this is what your break-even value is going to be, but you don't know theta, therefore, what do you do? You have this is the posterior distribution of theta given x and n for the consumer, which is given by that quantity now. Alpha 1, alpha 2 were the prior parameters. X is your updating being done by through x and n minus x. EC, this is the mean now. This is the mean of theta given x and n for the consumer. Expected utility of accept versus reject is bigger or smaller depending on this. Basically, you use this function here, A1, A2, A3. You can write down this form. You can convert the decision rule to whether or not when x is small or large, you accept or reject this. If x is small, you accept. X is large, you reject because x is measuring number of bad components are in. Yeah. Oh, sorry. So that's what happens. You can turn the rule in terms of some kind of a rule on how if x is small, you accept, otherwise you reject. Okay. On the other hand, this is making certain assumptions about the prior being conjugate form. I mean, in general, if the prior is reasonable, that's what you'll be converting to. For the M, manufacturers, if consumer accepts or rejects, well, if consumer accepts, that's your utility of the consumer manufacturer. If rejects, that's the utility over here. This N is taking into account what? N is taking into account the cost of experiment right now. Okay, and if this theta is bad, then basically consumer accepts it, but it's going to sell it to the consumer. Maybe there's some cost to be paid after by the manufacturer later on, because if it's a really bad product, there will be lawsuits later on. Okay, that's why you have to account for that. The quality level of the product goes into when the consumer buys it. If the consumer quality is really bad, theta is bigger, theta is equal to 1, then you may have some cost to be paid for by the manufacturer as part of potential lawsuits or damages or whatever else. Okay, so this is a simple example. I mean, you can do that for any complicated thing as long as you know the framework now. And so break-even value is there, but this again you don't know theta at all. So alternative values for A. So you can do other utility functions and go through this kind of analysis to find out what the rule is going to be for given x, and then what the corresponding utilities will be for both the manufacturer and the consumer. Now what do you need? But you need some kind of computer program to assess the utilities for M, for each value of n, and then you get the optimal solution basically. So I mean that's the step involved. You can do some examples where you give specific values for alpha, beta, and A1, A2, B1, B2, and solve it down. Basically, but you get something like the following. This is an example, nothing to do with any reality at all. The point. This is a framework in which you can solve the problem by specifying these utilities and then the priors, and it turns out for certain values of A1, A2, A3, it turns out the following happens. This sample size here, this is the M's expected utility basically for certain corresponding values. What happens for n is small, this is small. In fact, what happens when you go from 0 to something less than 6, you have a decrease in it. By saying if you're going to do experiment, just 0 observations versus 1, 2, 3, you're wasting your money. Don't even do the experiment at all. For small sample sizes, it doesn't pay off to do anything. It's better not to do any experiment. But once you do, the best thing is that over here, n equal to 6. That's the this is the maximum value. But this plot is not very good, but essentially this is maximum value. So you can find what n is maximum value, and for certain n values, initial values of n, it's not necessary that you'll always get increasing utility as n increases, because for a while n equal to 0 may be the best thing to do, because you're going to do a very small experiment. It's not going to change the consumer's opinion a whole lot, and therefore it won't be worthwhile to even try to do the experiment. That's why this happens here. goes up afterwards, and this is the maximum value. So this is the kind of thing analysis you can do by going through this kind of exercise. But then you have to be in a mode where you can communicate with the consumer and then assess these utilities and the priors and agree that that's what will be used in the decision making and then solve the problem. I think I'll stop at this point.